It's like we did last semester.
I think last year.
Yeah,
I didn't take it.
All right, that's 4 o'clock. Time to start. All right, first up, we have a couple of administrative things, just small things. One, first discussion is this Friday. We are having it this week. You'll get to meet our TA, Chloe.
Hi.
If you're in the night section, right? The later section?
The later section, yeah.
Yeah, the 2 o'clock section. Otherwise, we have our other TA. You'll meet them. I'll also be there. It's a lot of fun. Second, the UMass would like a course note taker for this class. Does any of you, if you take good notes, you can email notes@admin.umass.edu with the course number, section, and my name. If you do this, you get 1 credit or 45 hours of volunteer service up to you. It'd be cool to have that because then I can post the notes for everyone. If you're interested, do that. Otherwise, don't. Okay, so you also may notice that you all have a quiz. If you don't have a quiz, come grab one. Man my word, I did actually do a coin flip, and I think I would probably do this going forward. So luck was not with you today, or was it? There's a nice quiz. Yeah, take a quiz. That's cool. Okay. So now let's start with the content. So last time we talked about the function merge. Okay. Merge took in 2 lists, A and B. What do we know about these lists? Someone? They're already sorted. There's an important assumption about this. And it roughly worked. I'll just draw a picture rather than writing out the entire algorithm. If anyone really wants me to, I can do that, but I think all of you can write the code for this. Basically, I took my two lists, and one by one, I would compare the first elements of the list. Whichever was smaller would get added to my output list, and then that would be removed from the list, and I would compare the next element. So I would repeatedly do this, and what we ended up finding was that this would give us a fully sorted list. Now, what was the runtime of this? Can anyone tell me? In particular, how many comparisons did I make? There's a little bit of debate about this. Yeah, up there.
Minimum of the length of the...
So, there were 2 numbers that I talked about. There was n-1, where n is the... I'll use the length of A and the length of B. So it would be the length of A plus the length of B minus 1 was one option that we talked about. The other option that I mentioned was the minimum of the lengths. I know that not everyone caught the discussion we had about this, but can anyone tell me what this number is? Yeah. This is the max. This is the worst case scenario. How about this one? Yeah.
Best case scenario.
This is the best case scenario. So these are our bounds on the number of operations we do. Can anyone tell me what this would be if I say that the sum of the length of A and length of B is equal to n? Then what would I say about this asymptotically? What would I say it's upper bounded by? Anyone want to say? Yeah. O of n. So O of n is a nice bound on that. So if we all recall, this notation, this asymptotic notation, told us an upper bound on a function. So that is, if I have 2 functions, I'll use the colored. By the way, if you like the colored chalk, you can thank Jenna wherever she is for that. I appreciate it too. If we have 2 functions, if we had f of x and we had g of x, let's say g of x is like this, g of x, then under what conditions do we say that f of x is upper bounded by g of x? What does this mean? If I say f of x is upper bounded by g of x, that is, I use my asymptotic notation. What does this mean? What is this equivalent to? Can anyone tell me? In the back.
Okay.
So it's worst case. Yes, it is worst case. It's asymptotic worst case, but what does it mean numerically, I suppose? A little bit more specifically. Yeah.
That at a certain point, g of x is always greater than f of x, so linear.
Yes. So there is some point where after this point, as I continue on to infinity, g of x is greater than f of x up to some constant multiple. So that is, I'll write out the whole thing again, actually, just so that you guys have it in your notes again. You can use this formula for writing proofs, as we're going to need later on. we can say if f of x is upper bounded by g of x, this is equivalent to saying that there exists some point and not, so I'm calling this right here and not, and some constant multiple, both of these are just numbers, such that for every value greater than n naught, greater than equal to their equivalent by the way, greater than equal to n naught, we have, here I'll say on this side actually, sorry, we have that f of x is less than or equal to c times g of x, right? So what this looks like is as long as there is some point where beyond this point g is growing faster than f, is one way that we can think about it. That's the constant multiple comes out if we do that. So g of x is growing faster than f of x for every point beyond this crossover point, then we're good. And if we want to prove that some function f of x is upper bounded by g of x, we can just find some n0 or n naught and some c, and then if this happens to be true, if we can prove this is true, then we're good. We can also show that as n approaches infinity, infinity, so it's a bit weird. As n approaches infinity, we know that there exists, or sorry, I'll say they exist before, sorry, just be slightly pedantic. So we know that there also exists some c, such that as n goes to infinity, of the proportion of them, so g of x times c over f of x, goes to what? Where would it go to if g of x is an upper bound of f of x? Then as I take the ratio of them, what happens as n goes to infinity? You can think about it for a second. I'll let you guys think about it for a second. Okay, anyone want to give me the answer? Or a guess? It's fine to guess, by the way. Yeah, go for it.
We should go to infinity.
It goes to infinity. This grows faster than this does. G of x is growing faster than f of x. So this would go to infinity. The reciprocal would go to 0. Make sense? So we say that essentially the difference between them grows and grows and grows and grows and grows up to some constant multiple. That is, when I say up to some constant multiple, that means if I have the correct scaling factor, then this happens. Does that make sense? So we really care about essentially the derivatives of them. We care that one is growing faster than the other. Okay? That makes sense? Now, this notation is commonly used in computer science to talk about runtime and talk about memory, which is the way that we are talking about it here. But this is a more general notation. This is just talking about upper bounds and stuff. Here, we wanted to say, what's the upper bound on the amount of operations that I did? So I'm counting the number of operations. I can, say that in particular scenarios, I can count the exact number of them. I can say maybe it's n minus 1. And then I know, because every single one of these is upper bounded by O of n, then I know that all of them are. So I know that this is the worst case for my algorithm in terms of the number of comparisons I'm making. That makes sense? Sorry, I was a little bit word salad-y. Basically, I can count the number of operations I'm doing, the operations I care about. In this case, it's comparisons. In general, in this class, we're going to care about floating point operations, which is like addition, subtraction, division, etc. You can wonder about other operations we might do, like exponentiation and stuff, but we'll get there when we get there. We count how many of those operations happen, and then we give some asymptotic bound, and this tells us very roughly how much longer does this algorithm take as the input gets bigger. Okay? So importantly, this notation does not tell us the minimum amount it would take. It doesn't tell us on average how long it would take. It doesn't even tell us the exact amount of operations. So if I say it's O of n and I know this is a tight bound, meaning I can't, there's no other bigger upper or lower upper bound that's still an upper bound, then I don't actually know how many real operations it takes. It could be 3 trillion times n, or it could be 3 times n. Right? It doesn't really tell me that. So this is an extremely limited notation, but it's generally used to show that some algorithms have better behaviors than others. It's a very limited notation, but it's one that we're going to use, but it's good to keep it in your mind where the limitations are. Now, one way that we can fix this limitation is we can try to invent some idea of a lower bound. Anyone have any ideas how we might do that? Yeah, back there. Best case scenario. So that is one thing we could do. If we can somehow prove the best case of how many operations it takes, then I can have that number and that will be some lower bound on how many operations I can do. How about if I want an asymptotic one? Are you okay answering that?
Yeah, fine. You instead just have to take a similar approach where after a certain point it's always greater than rather than always less than.
Yeah, exactly. So we can say the same exact type of definition, except reverse. At a certain point, it's always smaller, right? You're going to get on the quiz, you're going to get to work with this. But for now, I'm just going to tell you that what we want to do is we want to, we're going to have a new notation for this. We're going to use a big omega, okay? One way, by the way, that should be good to remember this. The one way that I remember this for a while is omega kind of has a floor on it. You can see that it's a floor, it's a lower bound. Cool? Cool. So in this case, we would say the lower bound is going to be min of A and B. This is because I'm using this notation, this is valid. The reason that I'm saying this is because I don't know how long these are. I have no guarantees about them being order of n. They could be order log n, like one of them could be significantly smaller than the other. One could be some constant length. I don't actually know. So I'm going to say that's the order of that. Now, would it also be appropriate to say that my algorithm is lower bound by, let's say, 1? This is the notation, by the way, for saying some constant number. Right? Would it also be appropriate to say this? Okay. I'm seeing some yeses. How about, raise your hand if you think the answer is true. It is. How about false? Okay. Okay. So it is, in fact, going to be the case that we could say that this is lower bounded by this also. For one, constant is going to be sort of the lowest ever, because I can always scale it down all the way there. I suppose there would be like 0, like take 0 operations, but we're going to say constant is like the lowest generally. And similar to the way that we defined the upper bound, this is not necessarily a tight lower bound. Anything that is a function that grows slower would be a lower bound. So both of these are loose in some way. Okay? I'm going to prime you with all of that. On the quiz, you'll get to explore this a little bit more. Yeah? So far, that's all we've defined. We will have other definitions, but so far we've defined a loose upper bound and loose lower bound. Again, both only asymptotically. It's only saying as n goes to infinity, is one bigger than the other, not in the actual world. It might be that my n naught has to be 100 trillion. So in the real world, our numbers are never going to be that big. Yeah.
So asymptotically is like
Yeah. So asymptotic means as we approach infinity. That's like the meaning of asymptotic. I'm hearing a lot of ruffling in my shirt. I want to change that. I might just turn it off for now. It might ruin the recording, but we'll see. It's bothering me. I'll just speak up a little bit louder for everyone. Okay. So we have these tools, and we have this first algorithm. We're going to put it together into a very nice algorithm, okay? It's one of my favorite introductory algorithms. You saw it on the bonus question on the first quiz. We're going to somehow use this function to give us a sorting algorithm, okay? Anyone have any initial ideas? I know some people who filled out the bonus do know the answer already, but if you haven't worked it out, I want you to think for a minute how we could use this function to sort an arbitrary array. Not given it in sorted order, obviously, but I want to take an arbitrary array and turn it into a sorted array just by using calls to this function and some other stuff. So genuinely think about it for a minute. Maybe if you've already known the answer, you can appreciate the answer for a minute and think maybe about the runtime of it under these. Take place. All right. We have plenty of time to talk about this in the future and think about this. This algorithm we are going to call merge sort. Okay, it's a very famous algorithm. You'll be able to find it online everywhere. You'll be able to find it in lots of textbooks. And we're going to say that it's just going to take some array. Some list, whatever data type you prefer. Okay. And the basic concept behind this works something like this. Let's imagine, instead of taking an array, I take a whole bunch of different numbers. Okay? So let's say I have all of my numbers. Let's say I have like 3, 1, 2, 4, 6. Okay, I have all these numbers. Okay? And I have them all now as their own arrays. Okay? Now what can I do with merge? Any ideas? Yeah, and far back over there.
Create numbers.
So kind of, but there's something specifically when I have this input, what could I do immediately? So what I could do is I can I'll add an extra one just to make it simplified. I'll make more just to make it extra simplified. 5. Sure, something like that. So I'll have 8 of them just so it works out very nicely. What I can do is I can call merge on every pair of them. If I call merge on this, what am I going to get? 1, 3. Okay, cool. How about this pair? 2, 4. Great. How about this pair? 6, 8. And this pair, 5, 9. Okay. Now what I can do? Any guesses? I do it again. So I can take these two, use my merge again. What do I get? I get 1, 2, 3, 4. Do with these, I get 5, 6, 7, 8. I probably should have spread them out a little bit more. 6, 7, 8. And then combining these, I end up with my full sorted array. So this is the fundamental idea that we're going to be talking about for the first session of the class. This is called divide and conquer. Okay? The basic premise, I divide up the problem into as small a problem as I can and define how to handle that base case. And then I recursively call some way to handle those smaller cases to build up bigger and bigger and bigger into the main case. Now, this is one way to notate what I'm doing here is I'm saying I immediately just split it into smaller bits. But this doesn't always work exactly this way because it might not be obvious how to split them. Obviously with merge sort, we're going to just look at this example for now. I'm just trying to prime you that it's not entirely the full story because it might be difficult to decide how to split a problem. If I have a graph, it might not be clear how I split up a graph into different parts. If I have a tree, it might not be clear. I mean, tree is pretty easy, I guess, but other examples, you can see it's not super clear how I divide them. So a divide and conquer algorithm is going to be divided into 2 steps. I'm dividing the divide and conquer. First is going to be how do we divide up the problem recursively? And the second is going to be how do we recombine them? How do we conquer them? Right? So with the merge sort, really we can think we have our full array. I'm going to subdivide it over and over until I end up with my unit components, my base cases, wherever they are. And then I'm going to recombine them. So then I can conquer them by recombining them into larger chunks, and finally into the solution to my problem. As with every type of algorithm we're going to talk about, this is like sort of outlines of types of algorithms. So like a divide and conquer algorithm, there are a lot of problems that divide and conquer are very good for. Of course, you can use multiple different techniques to write algorithms for different things, but a lot of problems have very clean solutions like this. But it's not a one-size-fits-all situation. This is very much not a, oh, here's the outline, everything will work. Sometimes it can be much more complicated than this. In the discussion, so merge sort is a very clean, beautiful type of algorithm for divide and conquer. In the discussion, we'll look at another divide and conquer problem that's slightly less beautiful. And you'll get to see how it happens in practice. Now, first off, how do we prove correctness of this algorithm? I think I've justified it to you. I'm not going to write out the pseudocode fully because I'm going to trust that you guys could do that. Basically, I just need to find the middle point, divide it, and then recursively call on those divisions on this. There's several ways to code this. There's a pretty beautiful recursive version. You'll see on the quiz some way that you could do this perhaps. So you'll see an example of pseudocode on the quiz, but for now I'm not going to write it on the board just because it's slow. But how would I prove correctness of this? Anyone? How would I formally prove correctness for this? Yeah?
By induction.
So do it by induction is a reasonable way to do it. I would suggest that the first step that we should do is actually prove correctness of merge. So I've sort of made the assumption that we have the proof of correctness for merge. But let's say first we can do merge, right? And how could we go about doing merge? Any technique that we might want to use? I said induction, but I think I'll actually go with contradiction just because I personally like them better. Induction works just fine. I outlined it a little bit, but I'll be slightly more formal today. In lecture, there's another point that I want you to take away from this. In lecture, I won't be able to be the level of formal that you'll need to be on a lot of the assignments that you do, just because I'm up here on a blackboard with a time limit trying to talk about a lot of things. For you guys, you should tend towards the end of more formal. You should be more specific about the things that you do, be more precise with your logic and all of that stuff. I'll try to give you a rough outline of the actual logic, though, that we use. So, for merge, so we first can prove correctness of merge. With merge, I have my two sorted arrays, and then I end up with some array. And to set up this contradiction, what I'm going to say is that this array is not sorted. And I'm going to attach that to another. So first I'm going to make the assumption that this is not sorted. And to do that, I can make a secondary assumption, which is that there are two elements, let's say x and y, that are adjacent and are not in sorted order. Okay? So I've changed it from this broader assumption that this is not sorted into something more specific, that these are not in sorted order. And then I can look at my actual algorithm and make a little case here. So when I'm adding x, right, I must be comparing 2 points. And either y is, so if I'm comparing x, then y is either this point or is this one. Okay? So because these are in sorted order, and I've now said that y is smaller than x, and this is already in sorted order, it cannot be that one. Okay? Secondly, when I'm adding x, the one that ends up in this index, when I'm comparing them, is the one that is lesser of the two by definition. So because both of those cases are not true, there is no possible thing for y to be. It can't be one of the two options it can be. That means that this is going to lead to a contradiction, meaning that my assumption was false, and therefore this does in fact produce a sorted array. Does that make sense? This is again just like an outline of the argument. You'd have to do this all with formal logic, but hopefully you understand the key pieces of this. We'll give you plenty of examples of doing formal proofs, and I will do some out in class later down the line, but these are fairly easy, so I'm going to not spend too much time on them. Do people all understand this? Can I get a thumbs up or a thumbs down if you understand this? It's okay if you don't. I just want to know for my own sake. Okay. 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 All right. So we'll get back to doing some proofs later on, but just for now, the overall outline of how we're going to be proving merge sort and divide and conquer algorithms in general is we're going to prove some component, the recursive step, we're going to prove that correct, and then that allows us to do either induction on this, or we can similarly do a proof by contradiction. So now we can apply the merge here, and we can say, if I'm defining in such a way that I pre-split them all, then by the definition of merge and by the correctness of merge, it will lead me to the conclusion that in fact this will be a sorted array. This is again slightly hand-wavy. In practice, what you need to prove is either set up an induction or set up a formal contradiction and get it to the conclusion. Okay? Again, I'm hand-waving this a little bit. Proofs, we're going to cover several times throughout this class, but we're only going to do asymptotic runtime basically once, and it'll come up throughout the class, but I'm going to focus on that instead, okay? So, let's talk about the runtime of this. Can anyone tell me what the runtime of this is? By runtime, I mean number of comparisons I make. So in each one of the merges, so merge, right, remember, merge was upper bounded by n, okay? Cool. So then, merge sort, how many times am I doing merge? Yeah. So I'm doing it log n times. We'll get to that in a second, but yeah, we're going to do it log n times. So why are we doing it log n times? Can everyone think about that for a second? Give people a second to think about it. Yeah? So each time I'm dividing it into halves. So the number of times that I'm doing this, I'm doing my divisions, is pretty obviously log 2n, roughly log 2n. It could be that there's some odd section that goes one longer. Log 2n, and then every merge step, I'm combining two things that double the size roughly. So once again, this is going to be log 2n combinations. So I'm running merge this many times. All right, not exactly that many times, but I'm running it, like I'm doing that many phases of it. But then how many times am I running merge on each one of these? Or, okay, different question, I suppose. If I have these, if I'm at this stage right here, where I have them all divided into individual elements, how many individual times am I running merge? So I'll draw this a little bit differently, actually. Here. I want you to think about the question. Okay? So I have all my individual elements, whole list of them, however many, and all of them are getting paired together. Every pair is running merge sort, or is running merge on it, right? So how many times is merge being run? Yep. So it's being run n over 2 times. And how big is each one of these arrays? It's one log, it's constant time. So the sum of the two of them is what? It's 2. Remember, the runtime, I'll make it different so it's more clear. It's going to be the length of A plus the length of B also. That's what I defined as n previously. So this is then going to be 1 plus 1 for each one of these. So it's going to be n over 2 times that I'm calling it, and each one of those is going to take 1 or 2 comparisons, depending on how I want to define it. But it's going to be times 2, basically. Okay? Okay, then I'll end up with half the number of them, right? So how many times am I running the merge? Yeah? What?
Times 2.
So it would be times 1, actually, because so I'm saying that it's order of the combination. So this is like order 2. If that makes sense? No? Okay. So the number of comparisons when I'm comparing these two, it's going to be 1. So I think it's fair to say 1. So I'm calling it that many times, I'm doing times 1. I'm saying that 1 is order 2. Which is, sorry, that's a little bit wacky to say. I know that you guys aren't super familiar with this, so sorry for that little bit. But it'll be 1 comparison.
Okay, that makes sense.
Cool, cool. All right, how about in the next phase? So now if I split them, okay, how many times am I running merge? I want a new hand. Maybe someone here in the middle. You're not enough in the middle. Anyone? Now think about it for a second. So if I ran here, I have, I have n different elements. Every pair of them I did together, that is, I would have to call merge n over 2 times, every pair. Now, every pair produced a single list, right? And then I combine each one of these. How many of these combinations do I need to do? Yeah.
N over 4.
It'd be n over 4, because it would be half the number of the previous step, right? Because every pair became a single array, so now each one of those, I just need to combine once. So it'd be n over 4, and how much time would it take for, how big are each of these arrays? Or what would be A plus B of this, minus 1? Yeah. So they would each be 2 long, right? So the number of comparisons I need would be 3. Would be 3 comparisons for each one of these. Okay? So now as I take this, as I do, let's say, any different, like A steps of this. So let's say I do this A times, then what would this be? So how many times do I run merge after A iterations of this? 1 new hands also still. Yeah. Oh, sure. Yeah, go for it. So it would be n over 2 to the power of a, because each one of these times I have half the number of them, right? And how many comparisons would I need to make? Give everyone a chance to think on it, yeah. A. Alright, so it would, no, it wouldn't be A. Yeah. And so sure, you see me here. Not A minus 1. No. So not quite. You seem excited to say it. Sure. It'll be 2 to the A minus 1. So remember, when I merge two lists, the resulting list is double the length, right? If each of them are the same length, then the resulting combined list is double the length. So each one of these phases, I double the length of the list, and I also have the number of these that I do. So this will be, the first time it'll take me, I'll do n minus 2 calls to merge, and I will only take one comparison per, and so on, and this will be, I'll write it like this actually. So it'll be n over 2 to the a merges, and each one of them will have 2 to the a operations. Comparisons in this case. Does that make sense? That we're each time the arrays are getting twice as long. Okay, so that is the number of operations has to double each time, and the number of merges that we're doing is halving each time because we're combining them each time. We're having the number overall. Okay? Yeah.
I don't understand
The amount of comparisons. Yeah, and we found that previously the comparisons was order of the two lengths combined. Right? Is at least going to be that. Yeah. It's going to be order of that. Yeah. Cool.
What would you say A is?
What would I say A is?
Yeah.
So A is just a random variable that I came up with. I'm saying after I do A iterations of this, after I call recursively A times, if that makes sense,
Yeah.
then this is what I would end up with. Okay? So this is going to be the first way that I'm going to say this. Okay? And then I'm going to do this another way, and it will maybe be more clear for the people who didn't get it the first time. And then we're going to be able to do some analysis on this. Okay? So now I'm going to actually write out the function. Yeah?
Shouldn't it be 2 to the minus 1?
Yeah. When we're talking asymptotics, we usually don't care. But yes. Here you go. Correct. Yeah, when we talk asymptotically, we don't care about individual operations in general. But if you're being precise, if you care about the exact number of operations, which is a perfectly normal thing to care about, it would be minus 1. Although we'd also be careful because the lower bound is actually slightly lower. So anyway. So now let's look at a way that we could actually code this up. Okay? So we get our array. Okay? And we have a base case first off. If my array is only 1 long, what do I do? Yeah, cool. So if the array, I'll just call it A to make my life easier. Let's make it A. So if the length of A is, let's say, less than or equal to 1, then I would just return the only element in A. I'm ignoring a bit of an edge case where I get an empty list. I'm going to assume that I don't have an empty list just for the sake of it. And this is going to just return the only element in A. Cool. That's everyone happy with Python notation for the pseudocode? Cool. So then, if I don't have that list, right, what could I do? So how could I phrase this? So the previous version that I talked about was, let's assume that we just have individual elements and I'm only doing the merging. But if I'm starting with the array, then I have to do both. And there's a bit of a clever way that I can do them simultaneously. If that makes sense. That I can just do recursive calls. Anyone have any idea? No. Yeah. So exactly. So what we're assuming is that merge sort is going to return a sorted array if I give it an array, right? Cool. And we know that in the base case it will do that. We can even make our base case here. How about this? We'll make our base case like this. If I make it less than 2, then I will just return Python sort of A. Cool. To make it very clear, I will if I have 2 elements, I will sort them into the right order. Okay. Cool. And now what I can do is I can divide it, and then I can recursively call merge sort on it. Okay. Does that make sense? And I will return 2 sorted arrays, and then what can I do with those sorted arrays? Merge them. So what I'm going to do is I'm first going to find some midpoint. So the midpoint is just going to be the length of A divided by 2, let's say ceilinged. Just, we can choose either ceiling or floor. I'm choosing the ceiling of it. Everyone okay with that notation, by the way? Just making sure that no one really, I can explain it if anyone doesn't understand it. Yeah? Ceiling is round up to the nearest integer. So when I say this, I'm just raising it to the nearest integer. Cool? Cool. All right. So then, what I can do is I can return sort of the left-hand side of the array. So this is like, if I have my array, I'm finding the midpoint, and then I'm going to split it into 2 different arrays. So my left array is just going to be all of the elements up to the midpoint. So this is going to be left, and this is going to be right. So my left is just going to be A from 0 all the way up to the midpoint. Here, not inclusive. I am not being precise on my off by ones, by the way, but you should when you write your algorithms. Next is going to be right equals A of mid to the length of A. Cool. That makes sense. Okay. Okay. We happy with this? We happy with this? Okay. Cool. And then what I can do to them, I can sort each of them. Right. So I can do. When I sort them, all I need to do is recall merge sort. Right. Yeah. No. So you're saying this or? So no, actually, because it's not inclusive. This indexing. Yeah. So it doesn't include the final one. So it's actually it is fine like this. If you really want to be to make sure though, this indexing does actually work in Python. You can just do this, and there you go. But yeah, no, it is actually correct the way that I had it. I'm not off by 1 on these, but if I ever am off by 1 on the board, I tend to not care too much. But be precise when you're writing your own algorithms on pen and paper. Anyway, so then if I want to sort each of them, I can call merge sort. So this is a very similar line of thinking to induction, where we assume that our algorithm works. We know that it works when I get small enough. I'm going to do merge sort now on my smaller elements. That makes sense? So I'll say like, maybe like sorted L is just going to be equal to merge sort, sorry, it's losing a little bit of space here. Merge sort left, and then sorted right is going to be merge sort right. Okay, and what is the last step that I need to do? I want someone that hasn't raised a hand yet. What's the last step? Yeah, Sunny.
Merge, sort,
But not merge sort,
merge.
just merge. So remember, we've already previously defined merge as this algorithm. Now I have 2 sorted arrays. This is sort of like an inductive hypothesis or whatever, where I'm assuming that they work correctly. And then finally, when I do my merge, so I'm going to be returning this also, I guess I should say. Returning merge sorted left, and sorted right. Okay, so this is the full sorted version, and what you see here is the number of recursive, so you see I'm splitting in half each time and calling the function again, and I have some amount of operations that I have to do at each one of these steps. Yes?
Like, I get from merge sort is like taking it and like sorting it in pairs.
Yeah.
Like, for example, if you have like sorted L equals like 2, and then sorted right is equal to like 0, 1, then how would I put it together?
It will put 0, 1, and then 2,
Oh,
3.
very
Yeah,
specific.
because it will just compare them. Yeah, so it's fine if they don't overlap at all. That's totally fine. If one is totally smaller than the other, merge works fine. Okay, so now what we're seeing here is that each one of these iterations, I'm splitting it in half, right? And then I'm running merge on these 2. Okay? So I run merge on these 2, then I'm going to run merge on each one of these pairs. So I'm going to run merge on these after I do my sorting, and I'm going to do the same here, and so on and so forth. So this is a recursive algorithm, right? So I'm going to recursively call things, and every time I call it, I'm going to call it 2 times on arrays that are half the length. Okay? So one way that we can think about this is we can actually write a recurrence to count the number of operations I perform. Okay? So the common notation for this is T of n. So T of n is going to be our recurrence, and we want it to capture this behavior somehow. Okay? We want to capture that it's splitting it in half each time, calling itself twice. So it's calling itself twice on things that are half the length. So any ideas how we could write that mathematically? Sure. Yeah.
2t n over 2.
So exactly. So we're calling it twice. So we have 2t, right? I'm calling itself twice. We'll say that each, like, this is essentially like merge sort, except this is just counting the number of operations I do. So I'm calling it twice, and I'm calling it on things that are half the size. Okay? Is this enough? Does this capture all the operations I do? No, this doesn't do anything. What I can do instead is I can say in each one of these iterations, each time I split it in half and I do this operation twice, how much extra work do I have to do? And what's the extra work that I do here? So I do my splitting, I do my recursive call. What else do I do when I call merge sort? Sunny? Merge. So I do merge, and we know the runtime of merge. What's the runtime of merge? Also Sunny. O of n. O of n. So exactly. So each one of these iterations, I need to do a merge, and that will take order n runtime. Okay? Does that make sense? So each one of these, we can look at some iteration of this. Let's say I go twice. Then each one of these are going to be 1/4 the size, right? And I will do 2 to the 2 of them, so I'll do 4 of them. For these individual arrays, I'll do 4 combinations of them, and each one of those will require 1/4 the amount of time. It will require O of n over 4. Does that make sense? Yeah.
So the recurrence also for operations.
Yes. So this is a function that is the number of operations done by our function, by merge sort in this case, and we're just putting it in a form where it's all things we know. Right? We're splitting it in half each time, and then each of those splits is going to be half the size, right? And then in each one of these iterations, I'm going to do a merge that's going to take O of whatever that size is. That make sense? We can even say, if we'd like to, we can replace this just with, instead of saying O of n, which is, I know is notationally weird, I can just say like n or n minus 1, as someone else pointed out before. To make it slightly more palatable, perhaps. Okay? We know that's O n, but we just say n is fine there. Okay. So then how could I work out what this is equal to? So at the end of the day, what I care about now is showing that this is upper bound of something. I want to say this is something. Right? T of n is not a proper thing for me to say. So how can I get how many operations I actually use? Any idea? You're lowering your hand?
No,
No? Okay. No. Okay. So, yeah.
The size of the
I can't hear you.
the size of the list hits 1.
So we should in fact have a base case on this also. So you'll notice this will recur infinitely at the moment. There is no end point. So we also do need to say like T of, in this case, 2 is just going to be a single comparison, for example. So we do also need a base case. That's good. Now there's a couple ways that we could solve this, but I'll show you my favorite way. So we can just directly solve this actually. It is possible that you can do it out each time, and what you'd end up with is something similar to what I said before of 2 to the a times t of n over 2 to the a, something like that. And you can just solve it directly, but there's a nicer way for us to do it. This is my preferred way of doing it. I'll call it like a computation tree or something like that. The way that we can do it is we can just look at each one of these as individual recursive like layers, right? So this first layer, this is like when I'm combining the two half-long arrays. How much work does that take? Or how many comparisons do I have to do? This is when I'm combining the two half-long arrays. I know you guys got it. I want to make sure that other people understand it. So if I have two arrays that are half long, what am I doing? I'm merging them. How many operations does that take? Yeah.
Is that half long? That's n by 2.
Yeah, n over 2.
N minus 1.
So it would be n over 2 plus n over 2 minus 1 is going to be n minus 1, or as I'm going to call it, just n for now. Of course, there are the minus 1s, but again, we're not going to care about them asymptotically. We mean n operations there. How about the next layer? Okay? So now this is when I'm combining each of the fourths. How many there? So how many times am I doing merges? I'm doing it twice. I'm merging each one of these. Okay? And how long are each one of them? So these are, let's say this is n over 2, n over 2. This is n over 4, n over 4. By the way, maybe some of you are confused about why I'm putting the n on this layer rather than the next layer. Doesn't particularly matter. That was just saying, like, there's different ways we do it. I would say it's here. There's n work there. Okay. So then how about this layer? When I do all of my merges here, how many comparisons do I need? Gosh. N over 2. So when I have the two n over 4s, how much is that?
At the 2 n over 4.
So adding the two n over 4s gives me n over 2. And how many times do I do it?
So it's n.
So it should be n, exactly. So each one of these is n over 2, but I do two of them, giving me that there's n amount of work done on this layer too. Now what we find is as we continue to split, how many work is done on each one of these layers? How many calls do I make to merge in each one of these layers? I'll let you say this one. You seem to be containing yourself. Yeah. How many calls to merge am I making on some arbitrary layer, some 8th layer, let's say? So no, that's the amount of total work. I'm saying the number of calls. When I go down like a times, right? Then how many is it going to be? We already did these. So when I do the 8th layer, it's going to be 2 to the a, right? And then the number of so that's the number of merges, and each one of the merges is going to be n over 2 to the a size, meaning that each one of these is going to be n. Okay? So that makes sense. So every single one of these layers, I do exactly n work. And how many of these layers are there? Someone I haven't seen before. Sure. Log n? Exactly. So there's going to be, again, there's log n total here. Log n total here. And this is going to be the number that I do. So at the very end of this, we can solve T of n is equal to what? If I do log n iterations of this, and each one has n, what is the total? N log n, exactly. N log n. And while I am ignoring the minus 1s on each one of these, say if you would like, you could do this as n minus 1 times log n. But this is an exact value. This isn't an asymptotic thing. This is just going to be the actual number of comparisons we make. And what is this upper bounded by? There's by a lot of things, but an obvious thing is, sure.
Just n log n.
Also just n log n. N log n. And any guesses what it is lower bounded by? Sure. Also n log n. And this is going to give us our final asymptotic definition that I'm going to care about for now, which is if it is both upper bounded and lower bounded by something, then we say it is tightly bounded by that thing. And we're going to use this notation, big theta, n log n. And for our analysis, when we're doing asymptotic analysis, this is the gold standard. We care about finding something that is asymptotically tightly bounded by some function. This tells me a lot more than either one of these do. Yeah, question?
Yeah, so I was wondering if like, one of the layers, one of these boxes doesn't have a huge amount of elements in that.
Yeah, so that is a nitty-gritty detail. It doesn't change the asymptotic bounds. That's the short answer. Long answer is that at each one of these layers, it's still going to be n, but the number of splits is going to possibly be different, and we may have like log n plus 1 because we might need one extra layer, something like that. It would be log n ceilinged is the number of layers we'd actually need. So small little details there. It doesn't end up affecting the asymptotic bounds, but good thinking. Those sorts of things can matter, but it doesn't matter here. Yes.
What about the difference between TNN and big data?
Yeah, so T of n is just a function that I came up with. We call it a recurrence. We're going to use the same notation on the quiz and in the future. That is a recurrence that is just me counting. So I'm saying I can, because the divide and conquer is done in such a systematic way, I'm splitting it in exactly these sized chunks. I can count exactly how much is done in each one of these layers, and so I can end up with a function that tells me exactly how many number of operations I'm doing. The big theta is an asymptotic bound. So that is not an actual number. Like T of n gives us the actual number of operations. This could be something wacky. This could be, 3/4 n log n squared. Like it could be something like that. Like it could be an actual number plus a whole bunch of junk, right? Whatever it is. But then we're choosing to write it as an asymptotic bound to sort of remove the junk and talk about how does it look asymptotically, and remove out the things that we might not care about. Of course, this still has the problem of this is only asymptotic. This isn't looking at real-world situations. We need to care about both, but for right now in this class, we're just going to care about this. Okay? Cool. Answer the question? Cool. Anyone else? Questions? You don't understand this? Yeah?
Can you just explain where the log n comes from?
Log n. So it's the number of times that I am recurring on this, and I know that each time I recur, it gets half as long, right? And if I want to know how many times I can have something until I end up with my base case of just one long, that would be log base 2 of n. Does that make sense? So it's how many times I can have it.
Yeah.
So that tells me how many of these layers I do. Does that make sense?
Yeah.
Cool. Okay. Good questions. I appreciate the questions. Yeah.
Like split it, so that's like the number of splits like earlier. And
Yeah.
Number 2a is like the number of layers.
So 2a, right, is the number of merges that I'm doing. So as I go deeper into this, I'm doing 2 times more merges each time, and those merges are of arrays that are half the size as the previous one. So that's where I get both of these exponents. This is, again, you could just work out this formula, and then you could say, I'm summing this log n times, and then I would get, n log n. That's a way that you could directly solve this, but this is just, I've made the realization that it's the same every layer. It isn't necessarily going to be the case, though. You can imagine some function that splits into 2 1/3 long chunks. How would I do the analysis there? That's something that we're going to look at on Monday. Okay, so it's about time now. Quiz. Do the quiz. Pull it out. By the way, don't forget to scan and submit your quiz. I reopened quiz 1 so that anyone who missed quiz 1 could still upload it. But don't forget this one. I'm not going to do that every time. So I'm going to give you like 5 or so minutes on your own first. Yeah.
I forgot to grab quiz.
Here.
Thank you. Keep doing it.
So long. Have you done it already?
Oh no, I handed mine.
There's another. Someone else needs one.
Oh, okay.
There you go. All right, starting now, 5 to 10 minutes, talk to people.
The maximum, whatever. Like what it takes to find that.
Was this intentional? In the middle doesn't actually make it in the middle. It's kind of like split. It has the middle still.
Still working.
It would take the max of
It's the same way you can always go bigger.
Best case scenario. That's the only one we didn't get. I'm not sure what we had. I don't know, that's what it was. That was he's doing it log n ways. He's still splitting it log n ways. Actually, no, he's not. It goes when it's so like minus right. So this right now. You'll actually be like so you split it twice. Just treat it like constant.
That one, like, it's the same number
Since it's always that, then log is going to be let's see, right? Top that always
You're saying, like, just log all the time.
I mean, to just log it. And if this log is
Like, one
I will let it slide a lot of the time, but
no, you can
there's like, and each time it's like 1 and then like 2 and then I mean it can still
like
I think just TO definitely basis besides just
I don't think so. Well, only log n
you want it to be like right in saying it's order as time 1 or it's constant.
let's see, let's sorting out that's just once you just go through all the elements
so it just be log
I think the
log n minus
it's constant shouldn't be just say like okay it's sorted it's like it's already sorted like it's kind of like easy
No?
That's why I say I feel like it's not sorted. Come on, with a radix.
I'm about to say, like,
sorry, what's it?
Radix. R-A-D-I-X.
only work with this one is like
Yes. I didn't say.
Oh, yeah. Just saying the same thing.
looking at it, I'm like, isn't it? I'm like,
really counts like in the best case like if it's already sorted then you only gotta go check this one is usually just the same.
This is weird. No, not really, because it's called
I mean, in an ideal world where it's already sorted, like I guess that's the best case. The amount of
Hear this out.
yeah, when it, like if you support it, it's gonna be like at least it's already sorted. I guess the best case is like where it's
It's on my like same.
like I said false, but I kind of like yes.
So we're going to do eliminate two of the elements.
Discussion of somewhere accessible.
You have two max and I feel like
The operations of which is like it's like something
Hey Max,
log down there. I think it's supposed to be a nice guy.
like if you go to the top of
It only has less.
Send it to you ahead of time. And I'll buy like one of you. Right now.
The two would just be
A minus.
so it would just like
Okay, all right. Coming off there. Let's go through the quiz. All right. First up. So this definition of asymptotic lower bound looks an awful lot like the definition of asymptotic upper bound. That's not coincidental. First, true or false? If f is upper bounded by g of n, it is possible that f is lower bounded by g of n. Raise your hand if you think that's true. All right. How about if it's false? Okay. It is in fact true, and here's an example. So in fact, what it means if it is upper and lower bounded by the same function, it means that it is as asymptotically tightly bounded by that function, which is an important concept, and we want to be able to have tight bounds. That's an important thing, even in like research and stuff. It's something we care about. 2, if g of n is lower bounded by f of n, that is equivalent to saying that f of n is upper bounded by g of n. Raise your hand if you think that's true. Okay, and false? Okay, that is in fact true. So a very quick proof for this is you can use the same, you can see the equation here for upper bounded, the condition, the logic for something is lower bounded. If you replace this with upper bounded and replace c with 1 over c, right, so you say that the constant for one of them is 1 over the constant of the other, then you'll actually see that the equations are equivalent, in fact. So, in fact, if something is upper bounded by something, then the other thing is lower bounded by it. So if one is bigger than the other, is upper bounding one, then the other is lower bounding or is smaller than the other. If that makes sense. Okay? Okay. Last of the true and false, and this is a hard one, by the way. Every correct sorting algorithm has at least a lower bound of n log n comparisons or a runtime for a list of length n. Who said true? Okay, and who said false? Okay. Anyone who said false want to give me an argument? Yeah.
For sorting algorithm that just checks linearly to see if a list is already sorted.
Okay, but will it sort then?
Well, that would be a best case scenario.
So you're saying, well, okay. I guess that's fair. So lower bounding isn't actually exactly best case scenario. It will be a lower bound, but it's not a tight lower bound. But that's fair enough. That's a sort of cheeky answer, but it's not quite correct. Anyone else want to give an argument? Yeah.
What if you apply the sorting algorithm to an already sorted list?
So the exact same argument there. You're saying the best case scenario would run in really low runtime. That doesn't mean that it's lower bounded by something. That means basically that all of them are going to take at least this much runtime. So in fact, those would not be lower bounded by n log n. Those would be lower bounded by O of n or O of whatever, which I guess is answering the question, but they're not, that isn't a, like, it isn't a tight lower bound. That's the argument, sorry. Yeah.
I was thinking that what if like spots of the array were already sorted, so you just sort the like you keep those in.
Yeah, so this they're all the same sort of argument here. So I think this is actually a little bit on me for calling the lower bound a best case scenario. That's not exactly accurate. What it's saying is that sort of every case takes at least this much time. That makes sense? That's what the lower bound means. Sorry about perhaps misleading you by saying it's the best case scenario. A best case scenario is a different type of analysis, and lots of them are just constant time. It's like, oh, the problem's already done. But that's not exactly their answer, yeah.
If you knew every time how much like every array is, unless it was too swapped.
So you're saying you, what do you do? If you knew all of the things ahead of time?
You knew like the amount of items in the array, if it was too, you could swap it.
Yeah, so again, this is, we were saying for an arbitrary length array though. That's making those numbers. I think these are all sort of the same kind of answer, is like you could hypothetically sort an array faster. But in fact, there are algorithms that sort arbitrarily long lists of things correctly in under this amount of time. Okay? Did anyone, so yeah, you have a thought?
Radix sort, because they use split.
So radix sort is an example of this. Radix sort is linear time. The difference with radix sort, can you tell me how radix sort can do better than merge sort? Merge sort feels pretty optimized. How does it do better?
Because it like sorts based off the least digits.
So yes is the short answer there. It is going to be okay. In short, the runtime of radix sort and some of these other sorting algorithms is dependent on the precision of the digits that we have. So if I know the range of my digits and I know that they are all integer, for example, then I can sort them very efficiently. Actually, so the way radix sort basically works, or one for just integer values, how it could work is I can count the number of occurrences of my digits. So I'd say how many times does 1 appear, how many times does 2 appear, etc. So in a single run through my thing, I can make all those counts up to some maximum value, and then I can just reconstruct my list based off of those counts. We'll talk a little bit more about radix sort and counting sort and all these other linear time sorting algorithms later. But just to keep in mind, there is a little trickiness here where a lot of times the complexity of my algorithm also depends on what type of input I have, what restrictions I have on my input. And I can actually get some benefit in terms of runtime and memory usage if I restrict what type of problems I'm able to solve. So radix sort and counting sort can only solve integer value or finite precision problems, whereas merge sort would work on any level of precision on my inputs. Yeah?
Given the work that sort is not considered a correct sorting algorithm.
So it is a correct sort. So the answer to this is false. So there are algorithms with a lower bound, but they have other restrictions on their array. Whereas merge sort is any type of values I take from my merge sort, it will work. If I have infinite precision, as long as I can check them in some finite amount of time, it will run in this amount of time, and it will run correctly. But for radix sort and other ones, if I have infinite precision digits or like floating point values, it'll take longer. Yeah?
Make it.
Yeah, no, so it would be, we can have less. We can have linear time.
At least digits.
So this is saying every has at least, and I'm saying one can be lower. Yeah, it can run in faster time. So it is in fact false. Last one, but I do want to talk about the other stuff. Yeah.
This is actually a question of the second false.
Yeah.
If something is like tightly bounded, like what is that? Or you're talking about like the limit approaching infinity or one or the other, like when they go so far away. If something's extremely bounded, then
Constant.
yeah, okay.
Exactly.
So it doesn't always approach infinity?
That's true. Yeah. Okay, cool. Yeah, it can approach the constant if it's tightly bound. That's a good point. I was just sort of making the point of it grows, but it could be constant. Okay, cool. I guess we don't really have time to cover the other written part here. I think it should be fairly clear. If you don't understand it, review it. And I will see you all on Friday. Goodbye. Get out of here. Go home.
I think that 11. the fact that this is number 4 or 5
That's math or business.
doing that thing.
My math major, I'm doing
Get stuck on that question. I mean, like,
The idea is that you're
sorry, I could not hear you.
Sort of. That's how I can come down.
Right, I was like,
It's
like why do you think
it's like
I have
one way that you can jump, analyze.
I realize it's like a strange thing to